All right, the last part of section 2.5 is a couple more theorems about polynomials, and then we're going to actually build polynomials. So we've been working to solve them before, but now what if I need to figure out what the polynomial is? So two things that we talked briefly about yesterday is the properties of roots for polynomials. So the first thing is that if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. Now, this is the last example that we did yesterday. We saw that this one had an x minus 2 squared factor in it. So even though we write 2 as a solution once, we have to count it as a solution twice because it came from a squared factor. That's how we ended up with a total of 4 solutions. So that's the first thing. The second thing, and this one is really important, is that if a plus bi is a root of a polynomial equation, then a minus bi, the conjugate, is also a root. Remember that imaginary roots, if they happen, are always going to occur in conjugate pairs, meaning you're always going to get a plus or minus. So if I just tell you one, you can assume that the other one is also a solution because they have to come in pairs because they come from taking square roots, okay? And then this fundamental theorem of algebra is kind of weird. It says if you have a polynomial of degree n, then the equation f of x equals 0 has to have at least one complex root. And you might be thinking, well, we've seen examples where we only got an answer like 2, 3, and 5. Well, remember that every real number can also be written as a complex number because the imaginary part could be 0. So that's why this theorem actually applies. That's not super important to know. It doesn't really apply to what we're doing, but it's good information. The linear factorization theorem says this. If you have some polynomial, then it can always be written as some set of linear factors, okay, where C might be a real number or a complex number, and it doesn't have to be a rational number. It can be something weird. So the idea is essentially that every 0 can come from a factor. And even if it's not something that's factorable, let's say that I have a factor like x squared minus 5. Well, we know that's not a difference of squares necessarily because 5 is not a perfect square, but I could still write that as x plus the square root of 5 times x minus the square root of 5 because the square root of 5 squared is 5. Think about if you solved this equation equal to 0, remember we would get plus or minus when we take the square root. So we could put those irrational numbers into our factors, and that's why everything can go down to a product of linear factors if you include imaginaries and irrational numbers in there. Okay, notice we are going to have some unknown leading coefficient in the front, and that's really the key of what we'll be doing in these problems. So we're going to look at 2 examples here of building a polynomial. So it says find a 4th degree polynomial f with real coefficients that has -2, +2, and I as zeros so that f of 3 is equal to -150. Now they give us a lot of information here and all of it is important. First is that this has to be 4th degree. That means we must have 4 solutions, okay? Well, they only gave us 3 solutions. They said -2, +2, and I, but remember, i's have to come in pairs, just like on your face. So if I is a root, then so is -I. So now we have 1, 2, 3, 4. And then this information is what we're going to use to find the value of A at the end. Remember, we said that's that unknown leading coefficient. So that's going to be the last step that we use. Now here's what I know. Based on those solutions, my function f of x that I don't know is going to start with some unknown leading coefficient a. And then because -2 and +2 are zeros, we know that we have the factors x plus 2 and x minus 2. And then because I and -I are zeros, we're also going to have x plus I and x minus I. Now, you don't have to multiply the whole thing out to write it in standard form, but you do want to get rid of the imaginaries because we can't really do anything with that. These are conjugates. So what we're going to end up with is a times x plus 2, x minus 2. And this is going to be times x squared minus I squared. You can do this piece in your head, but I'm going to write it out so we can see. Remember that I squared is -1, so this becomes x squared plus 1. And now we don't have imaginary numbers in there anymore. So that's what we want to make sure that we have. Now, the last thing we have to do is figure out what the heck A is. And that is going to be where we use this information because they gave us a function value. This says that when x is equal to 3, f of x is equal to -150. So we can plug those things in. When f of x is -150, that means that I used 3 for x. So let's plug that in. 3 plus 2, 3 minus 2, 3 squared plus 1. So -150 is equal to a times 5 times 1, which is 5, times 10. So that's going to be 50. So when we divide on both sides, we can say that a is equal to -3. Ta-da! So that tells us that our function, f of x, is equal to -3 times x plus 2 times x minus 2 times x squared plus 1. And that's a perfectly fine answer, unless it wants the answer in standard form, which means we have to multiply it all out. So if we need to do that, x plus 2, x minus 2 is going to be x squared minus 4. And then we can FOIL with those, so we get x to the 4th. Outside is 1x squared. My recording stopped somewhere, and I'm not quite sure where it stopped, so let's just summarize what we did here really quickly. So the first thing we did was we plugged in all the zeros to the factors. Remember that i's come in pairs. I know we got that far. Once we get down to the red, that's because I've gotten rid of all my imaginary numbers, and now I need to figure out what a is. And we use that information that f of 3 is equal to -150 to plug in and solve for a. Now, where I think this cut off was looking at the two solutions. The first way that we can write it is in its factored form. I would try putting that in MyMathLab first and see if it takes it. That would be a perfect answer for me. But if it's looking for the answer in standard form, you're going to have to multiply that out using FOIL and the distributive property, and that's how you get the final answer. So pause the video and try number 7 on your own, and I'll come back in 3 seconds with the answer. All right, so here's the setup. I know that -3 and I are zeros, so that means that -I is also a 0. Since this is a third degree polynomial, we want to make sure we have a total of 3 solutions, and we can see by looking at our factors, we have 1, 2, 3. So we have everything that we need. We need to get rid of those i's, so we're going to go ahead and multiply that out. It's the exact same one that we did before, so hopefully you can look at the previous example to see how we got x squared plus 1. And now we need to use the value that was given when x is 1, f of x is 8, to solve for a. So we have 8, and we don't know what a is. When we plug in 1, we're going to get 1 plus 4 times 1 squared plus 1. So that is going to be... oh, sorry, I'm getting ahead of myself here. I wrote down the answer. This should be 1 plus 3, and that adds up to 4. So we get 4 times 2, so we get 8a, which means a is just equal to 1. That's easy. So now to write our final answer, we know that f of x is going to be 1, which we don't need to write, times x plus 3, x squared plus 1, and you could leave it like that. Or we can multiply it out to standard form, which is going to be x cubed plus 3x squared plus x plus 3. And so that's it. Just make sure you remember that your eyes come in pairs. We're going to skip Descartes' rule of signs, so you don't need to do those last few examples, and they will not be on the homework or the test. I will see you later.